In this video, we're going to start looking at logarithms. In previous units, we've looked at exponents. I could write an exponential statement, and an example might be 2 to the power of 3 is equal to 8. We would say that 2 is the base, and 3 is the exponent. We might also call the exponent the power or the index. So we have now an example of an exponential statement. Another example might be 5 to the power of 2 is equal to 25. Or 3 to the power of 4 is equal to 81. We also looked at solving basic exponential equations. 2 to the power of x is equal to 16, and we wanted to solve for x. Well, we know that 2 to the power of 4 is going to give us 16, so x was equal to 4. And that gave us a nice integer solution. What happens though if we wanted to solve the equation 2 to the x is equal to 10? Well, I know that 2 to the power of 3 is equal to 8. I know that 2 to the power of 4 is equal to 16. So, the value of x will be somewhere between 3 and 4. At the moment though, we can't give an accurate answer for that value of x. This is where we use logarithms, or logs for short. Let's look at another example. Let's look at the value of a car. So the value, V pounds, will be its starting price, which we'll take to be £30,000. We'll have an annual depreciation of say 20%, and that will be a multiplier of 0.8, which we raise to the power of n, where n is the number of years. So if I wanted to find the value of the car after 1 year, n would be 1. 2 years, n would be 2, and so on and so forth. But what if I wanted to find the age of the car when it was worth £5,400? Or the age of the car when it was worth £6,800? This is where we would use logs. So for both of these problems, we would use logarithms. The log function and the exponential function are inverses. In this video, we're going to work through some basic notation and terminology and look at some examples of this. So let's go ahead and write now an exponential statement. Y is equal to a to the x. A is going to be greater than 0 and a cannot be equal to 1. I'll let you have a play around of why it can't now be a negative number and why graphing 1 to the x is pretty boring. So let's look at an example of this. So what we have is this constant. A is a constant and x now is our variable. So let's say we've got y is equal to 2 to the x. So this is a graph right here. Y is equal to 2 to the x. So in this particular case, a is 2. So we've got 0, 1, and we could see now that this models growth. What we can now write is the logarithmic equivalent. So we can write if y is equal to a to the x, we can state that log to the base a of y is equal to x. What I want you to do is just hit pause and take a moment to read this. If y is equal to a to the x, then log to the base a of y is equal to x. The logarithm is simply now the exponent a base is raised by to get a value. So let's go ahead now and write this in log form. So we can see the following. We've got that 8 is equal to 2 to the power of 3. So we could write 2 to the power of 3 is equal to 8. We could write now the log statement. So if we write the log statement, we can say log to the base 2 of 8 is equal to 3. This is just the exponent 2 is raised by to get 8. And that is the concept of the log. So all we're saying now is if I put the 3 just here, 2 to the third power is equal to 8. So this now gives us our general statement. If y is equal to a to the x, then log to the base a of y is equal to x. Let's go ahead and write some equivalent statements. So if I had now 5 to the power of 2, we know that's 25. Therefore, what we can write from here now is that log to the base 5 of 25 is equal to 2. The log is simply now the power 5 is raised by to get 25. So if we wanted to write now the other way round, let's say we had now log to the base 3 of 81, that's going to give me 4. If we wanted to write the exponential equivalent, we could say that 3 to the power of 4 is equal to 81. We can just now move this power here and say 3 to the 4 is 81. So these now are equivalent statements. Let's do another one. Let's say we've got now log to the base, and we'll go this time, we will have now 3 to now log to the base 3 of 27. So what is the power 3 is raised by to get 27? The answer is 3. Therefore, we can write now that 3 to the power 3 is 27. And that now gives us the equivalent statement. Okay, let's look at a slightly trickier example. Let's look at the following. Let's say we've got log to the base 16 of 4. So what power is 16 raised by to get 4? The answer is the 1/2 power. 16 to the half is equal to 4. Therefore, we could write now that 16 to the power of 1/2 is equal to 4. Okay, let's write another one. Let's go for now log to the base 2. We will have now log to the base 2 of 1/2. What power is 2 raised by to get 1/2? The answer is -1. Therefore, now our exponential equivalent is 2 to the -1 is equal to 1/2. Remember, this log is simply the power that we're raising 2 by to get 1/2. Let's do another one. Let's write now 4 to the power 3. 4 to the power 3 is going to be equal to 64. Therefore, we can write now that log to the base 4 of 64 is equal to 3. So log to the base 4 of 64 is 3. 4 to the third is 64, and that gives us now our equivalent. What I'm going to do is just do a bit of graphing. I'm going to draw now 2 different curves. I'm going to draw y is equal to 2 to the x. That's the first one that I'm going to do. Now that is going to look something like so. So we're going to come through, we've got this point, and that is going to be 0, 1. And we can see that this is going to grow. So this is 0, 1. Y is equal to 2 to the power of x. So if we consider this point right here, if x is 1, we're going to have 1, 2. If x is 2, we're going to have 2, 4. If x is 3, we're going to have now 3, 8. If we have this point right here, and let's say now we have x is equal to -1, we get 1/2. If x is equal to -2, we get 1/4. This now is the curve y is equal to 2 to the x. What I'm now going to draw is the inverse function. Later on, when you study inverse functions, you will see that this now gives us a reflection in the line y is equal to x. So what we're going to have now is the graph, and this graph is going to be y is equal to log to the base 2 of x. And we're going to consider values. So let's go ahead and put this on. So this one is y is equal to log to the base 2 of x. So let's look at this point right here. We can see that this is 0, 1. This is going to be 1, 0. Let's just look at that statement. If we have now log to the base 2 of 1, what power is 2 raised by to get 1? The answer is 0. In the same way that if we have now 2 to the 0 is equal to 1, we can see that these are inverse functions. If I now take this point right here, so if we have the point here, this is going to be now where x is equal to 2. So if I have now log to the base 2 of 2, what power is 2 raised by to get 2? The answer is going to be 1. And we can see how this now is a reflection in the line y is equal to x, and these are inverse functions. If we look now at the next one, and we will take this point right here, so let's go ahead and put in 4. If x is equal now to 4, we're going to have, and we'll put it just here, let's put x is equal to 4. We're going to have now the point 4, 2. All we're saying is, what power is 2 raised by to get 4? The answer is 2. If we look here, we're going to have now 3, and then we're going to have, so we're going to have 8, and we're going to have 3. What power is 2 raised by to get 8? The answer is 3. Now, if we went the other side, let's go the other side. So this point right here is going to be 1/2. That's the x-coordinate. So let's look at that statement. Log to the base 2 of 1/2. What power is 2 raised by to get 1/2? The answer is -1. So we got now -1. And we can see -1, 1/2, 1/2, -1. If we had now log to the base 2 of 1/4. What power is 2 raised by to get 1 over 2 squared? The answer now is -2. And we can see that we'd have this point right here, and this is going to be 1/4, comma, -2. So now we can see the relationship between the two. What I'm going to do is just start to look at a couple of the rules of logs. So let's have a look at this one right here. Log to the base 2 of 2 is going to be equal to 1. In general, we can say log to the base a of a is equal to 1. This is fairly straightforward. What power is a raised by to get a? The answer is 1. If we now look at log to the base 2 of 1, what power is 2 raised by to get 1? We get 0. Therefore, in general, we can say log to the base a of 1 is equal to 0. These are two rules that we will come to in later videos. I thought as we're here, we will introduce them, and hopefully that makes some sense. So we have two different graphs now, and we're looking at the log and the exponential equivalent. Let's just work through a few more examples, and then we'll go back to the original question I set. So let's now write the following. I'm going to have log to the base p of 1. What we want to do now is write log to the base p of 1 is equal to 0. We want to write now the exponential equivalent. This is the log statement. Therefore, we can say now that p to the power of 0 is equal to 1. If we had now, for example, let's say we had log to the base 3 now of 9, that is going to be equal to 2. We can say now that the exponential statement is 3 to the power of 2 is equal to 9. If I now write log, and I'm just going to write log 100. Now, log 100, this is something that we're going to look at later. When you have a calculator, and I'll grab one up, let's grab one up, we have this button. This is base 10, so log to the base 10. So if I put this in, if we have now log to the base 10 of 10, what power is 10 raised by to get 10? We would expect 1. If we now look at 100, we would expect 2. 10 to the power of 2 is 100. Now let's say we had now, and I'll put it in here, we could either put 0.1 or 1/10. So what power is 10 raised by to get now 1 over 10? We would expect to see -1. So -1. What about if it was 1 over 10 squared, or 1 over 100? -2. So when we have log, this is what we have. Now on the calculator, we can have different bases. So what I'm going to do is hit shift, let's just get that, we need that one. This will now give me a base. So log to the base 2 of 4. What power is 2 raised by to get 4? The answer is 2. What power is 2 raised by to get 8? The answer is 3. What power is it raised by to get now 1/8? This should give us now -3. So if we just put this in, we end up with -3. 2 to the -3 is 1 over 2 cubed, which is going to give us now log to the base 2 of 1/8 is -3. So now if we have this, this is saying log to the base 10 of 100. What power now is 10 raised by to get 100? The answer is 2. So that's just writing out now the equivalent statement. So if we wanted to write this out, we could say that this is going to be 10 to the power of 2 is equal to 100. So all we're doing is writing them out. If we did some other ones, let's say now 12 to the power of 0, we know that that's going to be equal to 1. Therefore, if we wanted to write now the log statement, we could say log to the base 12 of now, this is simply going to give me the power, log to the base 12 of 1 is going to be equal to 0. That is what the log is. It's that power right there that we raise the base by to get this value. If we look at another one, let's say we've got now 4 to the power of 1/2 is equal to 2. Writing now the log statement, we can say that log to the base 4 of 2 is equal to 1/2. In the same way, if I wrote now log to the base 2 of 4, that's going to give me 2. And later on we will look now at the relationship between the two. So let's go back and see if we can now answer the questions I first set. what we want to do is solve this particular equation. So 2 to the power of x is equal to 10. So we could write now that log to the base 2 of 10 is equal to x. So this now is the log equivalent. We're looking for the power that 2 is raised by to get 10. So what I'm going to do is just evaluate this in a calculator. So I'm going to put now log to the base 2 of 10, and we will get now our answer. And we're expecting it to be between 3 and 4. 3.32, and we'll say that's 3.32, and that's correct to 3 significant figures. So x is equal to 3.32, and that now is given to 3 significant figures. So we can see that we don't have to just guess or make some trial and error approach. Okay, let's go back to this one. Let's say now the value, and we'll have this, let's put this on, we're going to have now £5,400, and that's going to be equal to 30,000, and then what we're going to have is multiplied by 0.8 to the power of n. So what I want to do now is find the value of n. So what I'm going to do at this stage is divide both sides of the equation by 30,000. So what we're going to have is 5,400 over 30,000 will be equal to 0.8 to the power of n. So at this stage I can go ahead and solve this. I mean, in terms of this right here, we can go ahead and cancel down. So what can I do? I can divide those, so let's get rid of those. So we've got 54 over 300. We can divide both of these by 6. So what's that going to give me? 9 over 50 is going to be equal to 0.8 to the power of n. So what we want to do now is write the log equivalent. So if we consider now that this is the power the base is raised by to get the value, we can say now that log to the base 0.8 of now 9, and we'll write this here, 9 over 50 is going to be equal to n. And I'm just about to find now the value of n, and that's the number of years after which this car is going to be worth £5,400. So let's put that in a calculator. Now in terms of solving that, I'm not expecting you to go straight ahead and solve that. I'm just giving you some idea on how we can use these. So we've got 9 over 50, and again I'm working between fractions and decimals. It's entirely up to you. So we can see that's going to be 7.68 years. So after 7.68 years, this car now will be worth £5,400, and that again is to 3 significant figures. So if we look at this value, if I take that now, so if we work this backwards, what we've got then is £30,000 multiplied by 0.8 to the power of my answer. We're going to end up now with £5,400. So we can see by using the logarithm, all I've done is made 0.8 to the power of n the subject of that equation, and gone ahead and used the logarithmic equivalent to find the value of n. And that's one way that we could do this. Later on we will look at using different bases. Generally speaking, we use base 10 in this unit, and in later units we use base e, or the natural logarithm ln of x. Hopefully for now though, that's given you a good start and a good understanding of what a logarithm is. To recap, it's simply the power a base is raised by to give us a certain value, and it's the inverse function of the exponential.